Hello, I'm Eric Ramey from the University of Wisconsin-Madison, and I'm happy to welcome you to Abralin ao Vivo, Linguists Online. This is an initiative the Brazilian Linguistics Association is designed to give students and researchers free access to state-of-the-art discussions on the most diverse topics related to the study of human language. I'm very happy to give you Bill Idsardi from the University of Maryland here in a moment. The title of his talk is Time and Order for Speech and Phonology. I want to thank both Bill and the Brazilian Linguistics Association for collaborating for this event. I'm very excited about it. And I'd like to remind you that if you have any questions for Bill or about the topic, you can put them in the chat channel of the YouTube thing, and I will present them during the discussion section. So without further ado, I turn this over to Bill. Thank you, Bill.
Thank you, Eric. It's great to be here. I'd also like to thank the Oberlin people for hosting all of these wonderful videos. There's quite a collection online now, and I'm happy to be part of it. So I'll start sharing my screen here, and I think we can get going. So there, I think it should be, oh, does it show up now? Eric, can you see the screen now?
Yes, I can.
Okay, great. Thank you again. And so today, what I'd like to try to do is my overall goals are to connect linguistics with neuroscience. And so this will be in response to comments that David Puppel and David Embick have made in the past. And I'll try to sort of make at least a little progress toward their challenges. I'll do this by trying to propose some plausible data structures and computations for speech and phonology. These may be less familiar than strings, and I'll provide a few linking hypotheses about these. This is attempting to be as information preserving as possible as you go through the computation. And an important aspect of this is being able to encode incomplete information. That is, we'll have various sorts of underspecification. The innovation here is a kind of underspecification in time. Another goal that we have is to try to reduce the differences between quote unquote exotic morphologies and quote unquote regular morphologies. And in doing that, we would make the non-concatenative types of morphologies as easy to do as the concatenative ones. That would be the ultimate goal. We may not reach that, but we'll make some progress toward that. We also want a system that's not too powerful. I'm not going to say a whole lot about this today. It deals with something that is probably some sort of restricted first order logic, so it's not Turing complete. We can talk about this in the question period maybe. And so then we would also like to reduce the number of primitives that we have inside the system to a bare minimum. So that is, the proposal is to reduce phonology to its essentials. And the claim here is that for spoken language phonology, that would be events, features, and precedents, where we have a set, or if you don't like set theory, a plurality of events. So these are points in time. That's the way they'll be conceived of here. And those points in time, those events have monadic properties attached to them. That is features. So if something is true of the event or not. So these are the standard sort of phonological features. You can have whatever features you want. I'm not, I have opinions about that, but I'm not sort of pushing that particular question today. So for instance, like an event might be a round event, or if you wanted to have whole phonemes, it might be a P event, that sort of thing. And then the pairs of events can be related to each other, that is ordered in time, via a relation of precedence. That is, we can say event A comes before event B. And by this, we don't mean immediately before, or we don't mean that it has to be immediately before. So there are a number of notions that are similar in this space. So one is just the concept of precedence, that it just precedes it, but not necessarily immediately. On the representational side, we'll deal with what are called in the literature gappy bigrams, or open bigrams, and they will be sparse in the sense in that they may not be a complete representation of all the ones that are possible. This has to do with transitive closure and transitive reduction of a graph. We'll see that briefly in a minute. And so the idea is that we are actually going to replace the sort of strings and sets and successor functions with bags, that is, things that can have repetitions, so a set with repetitions or a multiset, and graphs that encode the precedence relation, which we will denote, as is usual in this business, with the less than sign. So A is less than B means A precedes B. It's true that for other modalities, especially sign languages, they'll need additional relations. So events in a sign language can have spatial relations in addition to temporal ones. And I won't have anything to say about that today. So this builds on work that Eric did in his thesis, and that was that Max Papillon also worked on in his thesis from last year. And so these will be, for the most part, depicted with directed graphs. And so in the directed graphs, the events correspond to nodes in the graph. The features will show up as sort of the labels inside the nodes. So you can have multiple features on an event, like that is monadic predicates. More than one monadic predicate can be true of an event. And then we'll have an arrow that will indicate that you can go maybe next from one event to another event. As you see in the diagram below for Helter Skelter, then you can follow this through and in fact make a loop in this. This was Eric's innovation in dealing with reduplication, which we will see in a minute. So these are the sort of graphs that we'll have. I'm going to be a little bit back and forth between using spelling and using phonological representations in the thing when it doesn't make any difference. So this one is a representation for Helter Skelter. Also important maybe is that the graphs will have special events, a beginning event and an end event, such that you have to traverse the thing from beginning to end in order to have a valid pronunciation. So the intuition is that this is a bit like traveling or trying to book a ticket on an airline routing system. So the idea is, and this was solved or whatever, there are a number of software systems to this. One is ITA software, which was bought by Google, which was developed by Carl DeMarkin and David Baggett, along with other people. And so the diagram that you see on the right here depicts like a small fraction of the airline routes that you can travel, and the goal here is to go from Boston to San Francisco, and you can do this through a number of routes through a number of intermediate cities. So you can have various kinds of equations to do on this to try to optimize for different things on those routes, but this will be sort of the same thing that we're trying to do here. So from Boston, you can travel to Dallas-Fort Worth, or you could travel to New York City, or you could travel to Chicago, or you could travel straight to San Francisco. And all of those are valid things. You could stop in more than one city. You can, if you're running a round trip, you can stop in the same city on the way back or not. So there's all sorts of routes that you can plot through here, which are essentially partial transitive closures over the graph. And for the notion that these are maps, that's a powerful idea that was pioneered by Tolman in the 40s. We won't have much to say about this today, but there are definite correspondences that one can draw. So the proposal is that this less than relation, and which I'll also say is maybe next, is going to be the right way to build these things instead of using the successor function. And there are a lot of precursors to this idea. So you have this idea inside finite state automata. It's like the dollar operator in XFST. The same sort of concept is used in automatic speech recognition lattices for possible word recognition, as Ken Church did in his thesis, for instance. It's also the same sort of thing that's used in process algebras or UML diagrams, which very much like finite state automata. And for the more specific proposal about bigrams, open bigrams, bigrams that are not necessarily adjacent to one another, you can find this in the visual word recognition literature, Carol Whitney's work, Jonathan Granger, and Magnuson's most recent thing is the time-independent string kernels. So TISC, he calls it. And you can find similar ideas in the computer science literature. So Maury calls them gappy bigrams, and in the bioinformatics literature, where they're called gapped K-mers or gapped Q-mers. Probably the basic mathematics for this you can find in an article from 20 years ago in the Journal of Machine Learning Research on subsequence kernels. And it also bears strong affinities to the work that Jeff Heinz has been doing on the subregular hierarchy. These are the strictly piecewise relations. And in fact, you can also find this with temporal logics. So there are a number of things that are sort of converging in this way on this representation of precedence. So turning now to the challenge that David Puppel and David Embeck laid down 15 years ago, which they called the granularity mismatch problem. You want to try to figure out how you could, with things we know about in neuroscience, represent anything of value to linguistics. And their point at the time was that there was just an awful lot of mismatch between the two sets of vocabulary. So what linguistics was talking in was not really what neuroscience was talking in. And some 10 years later, they said that the problem really hadn't gotten any better. And they gave another set of correspondences that you could think about, and the job being to try to figure out, like, what is the neuroscientific implementation of a distinctive feature. So we'll offer a few suggestions here for some of these things, and to try to link up some of these concepts on the neuroscience side with some concepts in linguistics. In particular, I will say or claim that the phonological features are to be thought of as complex spectrotemporal receptive fields. So these are the sort of feature detectors that you have in primary and secondary auditory cortex. And the idea is that there are, and they're for all sorts of auditory signals. So there are going to be particular spectrotemporal receptive fields that will yield what we would want as phonological features. So they can be tuned to some degree by experience, but I think an awful lot of this structure is probably there innately. That is, it's genetically pre-programmed. We will have loops of events, and these we are going to identify with certain sorts of oscillations. So in particular, the theta gamma nesting that you see in phonological recognition for speech signals, where the theta cycle is something like a syllable and the gamma cycle is something like a feature or phoneme. We will do event feature binding by coincidence detection, since it's pretty much the only game in town. And we will do sort of the delayed coincidence, which is going to be important for us, with a SYN-fired chain delay line. That is, we'll have neurons that fire along in a sequence, and in doing so, carry information forward in time. And then we'll allow activations over individual items. By collecting those up, we'll get a set with multiplicities. That is, the activation over each item is the number of times it occurs. And that's a bag or a multiset. And so then the idea is that phonological representation is ultimately a set of a bag of features, or phonemes if you prefer, and a set of bigrams, open bigrams. Okay, so as people who are old as I am know, there was a famous argument against this sort of representation, which was similar to the representation that was used by Rumelhart and McClellan to do past tense training with early neural networks in the mid-'80s. And Steven Pinker and Alan Prince had an argument against this, that the Wickel that the Rumelhart and McClellan used were not is sufficient to represent reduplicated items. So their argument was in particular against Wickelgren's trigrams, but as they explain in their article, you could extend this to n-grams. And so their argument was that things like Algol and Algolgol need to be distinguished in languages that have partial reduplication. And if you just list out the trigrams from these two items with the number sign representing the beginning of the word and the percent sign representing the end of the word, then you end up with the same set of trigrams. And so their conclusion was that you couldn't represent the difference between Algol and Algolgol if you use sets of trigrams. And nevertheless, lots of languages have reduplication, and you'd have to be able to tell when you are speaking or listening the difference between Algol and Algolgol. And so this was a failure of the system itself to make a basic distinction that all languages need to make. But the crux of the argument here is a set of bigrams. And so if you add some sort of representation to this, like a bag of phones or a bag of features, which we will sort of I identify with like an activation over unigrams, then you can do this with gappy bigrams without any problem. So then the representation for Algol is now sort of two pieces, a multi-set of phones that you see, and the bigram relation so that you can move through the diagram that's below. And so Algolgol is just a thing where you've gone through this more than once. So, so you've gone GAL twice before you go out. And this is represented by the number of times you see A's and L's and G's in the unigram representation. So you can say like how many circuits you did essentially by appropriately incrementing the number of times you saw A, saw L, and saw G. Okay, so this somewhat more complicated representation that has two pieces to it is sufficient then to get the difference between reduplicated and non-reduplicated forms. So the important thing was that if you only restrict yourself to a set of bigrams, which admittedly set of trigrams was what Rummel, Hart, and McClelland were doing, then you wouldn't be able to make this difference. But you can keep track of other information and in doing so, be able to represent them as different. You can also do it by simply giving yourself a bag of arcs. So if you're allowed to say, well, I went from A to L 3 times, I went from L to G 2 times, and I went from G to A 2 times, you can also traverse this graph by exhausting the multi-set of edges. And then this will give you Algolgol, and of course, just pull out one of the circuits for Gol to get Algol. Right? So either way, you can either like have bags of edges or you can have bags of phones. I don't think that there's a knockdown argument yet for which is the right way to do things, but you'll need some move from sets to bags in one area or the other. So we'll build some small circuits and show how we think this might be calculated. The feature detectors, as I said before, are spectrotemporal receptive fields. This is building on work by Shihab Shana and Jonathan Fritz and Dima Meskarani and Eddie Chang. We'll break them into two pieces. So manner detectors, this is building on work by Ken Stevens and Carol S.B. Wilson. And there will probably need to have hypercomplex cells too in order to recognize things like voicing in languages where the cues to voicing, as is common, are different in different manner classes. For instance, stops have a different cue, phonetic correlate of voicing than fricatives do in many cases. So VOT, say, in the stops, and the absence of periodic vibrations in the fricatives. So what we'll do is build a little model for syllable. So we'll calculate the binding information within a single theta cycle, and then we will extract the bigrams from that, and then you do morpheme matching on the extracted bigrams is the proposal. So here's sort of a cartoon picture of what SDRFs sort of look like. This is just made from Prot using the cochleogram function so that it's scaled with the response for the hair cells in the ear. So the frequency here is in bark. And then the red sort of bands here represent sort of the kind of little bits of spectrogram that you can see in a spectrotemporal receptive field. For clarity, I've made most of these 50 milliseconds long. But you do see spectrotemporal receptive fields that have varying sort of lengths to them. They can have all sorts of properties. This is not the talk to go into that, but the idea is that you'll be able to recognize phonologically significant features by ganging together the output of simple spectrotemporal receptive fields. For a recent review about the relationship to these sort of detectors and human auditory cortex, see this Fox et al. Paper from last year. And then they were able to sort of map this onto epilepsy patients who were in having electrocortical grid implantation for recognition of their epileptic seizures prior to surgery. So these are done with patients. So they found a kind of complicated set of results, but they argue that there is a spatial gradient along which the VOT detectors are aligned, and that you can find really ones that are tuned to detecting the voice, well, what's so-called voiced in English. And so the short VOT times and the long VOT times. So this is sort of represented to a degree with this. So if you want to know more about spectrotemporal receptive fields, that's a good place to start. So we will bind the features into phonemes. This is the same sort of thing that I argued with Nina Kazanana and Jeff Bowers a couple of years ago. And so there we said that what we meant by phonemes is bundles of features coordinated in time. And so the coordinated in time here is just going to be coincidence detection, that they happened at nearly the same time. And so that means, like, not exactly the same time. So whatever the temporal acuity of individual neurons are, and whatever you're getting with co-articulation smearing across the thing in the speech output. So we also need some sort of delayed coincidence in time, and we will do this really just directly implementing what Gallistel says is carrying information forward in time. That's exactly what we'll do. So we'll just have a string of neurons that fire in a sequence. And so we will control this with a clock, and the oscillation, the theta oscillation, the gamma nesting inside theta will be done with just a clock loop. And so the mottos here are really very similar to what has long been the goal in neural network research, is to find static fixed length representations of dynamic variable length input. And that's quite difficult to do. Essentially, I don't think it's at all solved for the syntax, but for phonology, there are a small enough set of fundamental elements that I think that we can get away with this. So static fixed length representations for variable length input, I think we can do that. So we'll show sort of some cartoons here. So here, this diagram has got sort of three pieces to it. We've got the spectrotemporal receptive fields at the top with the thalamic input to them. So I've shown sort of, just a node meaning manner. Now this would actually be several detectors. Same thing with place, and whatever other features you need in order to represent phonologically significant events. So these probably are tuned to some degree to language-specific settings. Exactly what that involves, I don't think we know yet. So I'm not committed to these being located in A1. It's certainly probably more likely that these are somewhere higher in the auditory system, so that the basic detectors that you see in A1 are gang together in various ways so that they can do interesting ways of finding place information, for instance. At the bottom here, we simply have this clock, which all it does, this is just 4/4 time for our purposes right now. So this just goes 1, 2, 3, 4, 1, 2, 3, 4. So this is connected in a circle. And so, when neuron 1 fires, it causes neuron 2 to fire, which causes neuron 3 to fire, which causes neuron 4 to fire, and then back to neuron 1 again, assuming that they have some sort of gamma cycle extent. Then, by ganging them up together into this syn-fired chain, then we'll get something that approximates a theta cycle from this. And then we're just showing this is to allow you to have some sort of resetting mechanism that comes in and will cause the clock to reset at some point. And then the middle field is really where the work gets done. So this is just a set of coincidence detectors. And so, for instance, you have a manner information and clock information coming in. So the numbers here represent what you saw at time period one at time period one, and then what you saw at time period one at time period two. And so the second number tells you what time period we're in. And the first number says where that information was coming from. And so you build a little tree, basically, and you just carry this information forward. So what you saw about the first clock cycle, what features, what spectrotemporeceptive fields you saw in the first clock cycle, that information will be carried forward to the second clock cycle, to the third clock cycle, to the fourth clock cycle. So this array of neurons that you have at the end is the collected information about whether in whatever the events were present at, that should be bound to the first clock cycle, even if that information came in at later points. And likewise for the second position, for the third position, and for the fourth position. So in some ways, this is a way of getting the kind of information that a system like Trace uses in order to put together the information, even though it might have been delayed in time. So even though we might have a burst, let's say in the first position, we might not get the formant transitions until the second clock cycle or even the third clock cycle, and yet those formant transitions are informative backwards in time about the segment that we want to identify with the first position. And so we're accumulating information about the first position as we go through this. Likewise for the second position and the third position. And so then this array of things that are in dark purple here, they're going to be the inputs that allow us to extract unigrams and bigrams from what we saw during the syllable. And so essentially, in order to extract the bigrams, we'll just have a 2D array of neurons. And, the only thing that's really significant here is the 2D array, not the labels. The labels are up there just so that you can sort of figure out where you are in the table. But the idea is that there will be, for the word spot, then there would be some neuron that would say, oh, I saw an S, and then later on I saw a P inside the same syllable. And it's also true that inside the syllable spot, I saw an S, and then later on I saw a T. So the things that are on here are the open bigrams that you would have for spot. We can do this by stitching the syllables together by basically doing matrix addition. So then to recognize these, you want to take the information about the unigrams that you heard, so the individual sounds, like sort of like an anagram representation of the sound of the word, and then you have the open bigrams that you saw, and then these will all, to a certain extent, activate all of these three words. But in this case, like this one will be the most activated because it shares all of the open bigrams that you saw in this case. So the idea is that the words are connected then to the open bigrams, and those will allow us to make forward predictions, for instance, within a syllable or beyond, and other types of things. So we are trying to find this in other species. So we have, in collaboration with other people at the University of Maryland, we've been looking at a couple of species of birds, one of which, the budgies, have much better recognition of sequences than the zebrafinch do, sort of surprisingly. And so then we are recording in secondary auditory areas looking for open bigram or even just regular bigram relationships where we switch out the sequence. So we have a background sequence A, B, C, D, E, and then we switch two of the interior elements and then see if they can notice that. No results to report on this yet, but we are trying to do this with animals that are known to be able to sing songs. It's certainly not the same thing as human language, but it could use some of the same neural resources. So the summary so far is that the idea is that the events, features, and precedents provide a reasonable basis for the neural circuits that we'll need for these sorts of things, and a good basis for phonology, which I'll turn to next. They allow vague representation. So like if you don't spot something, the open bigrams, you can still partially match on incomplete information. So it's sort of more resistant to deterioration than other sorts of representations. So it has some redundancy in it, and actually I think the redundancy is okay. And in some ways, this is similar to the D theory that was proposed by Hindle, Marcus, and Fleck for tree representations that allowed you to be vague about where the attachment of, for example, prepositional phrases was. So you could say, well, it's somewhere in here, and I'm not sure exactly where it is in here. And so you can keep this vague information going forward in a perspicuous way. We'll see similar things here. So the first argument that I'll offer is really sort of a math argument. So there are two main understanding of events within temporal logic, and probably the best resource for this is Ben Bentham's Logic of Time. There are understandings in terms of continuous time, and there are understandings in terms of discrete time. Now, so far I've been talking about it in discrete time, but Van Bentham considers both, and in that case, he points out that really only the precedence relation, the less than relation, the open bigram sort of relation, is adequate for both of these. And so the definitions that he gives for the discrete representation is an ordered couple. So we have a set of events, T here, and a binary relation of less than on that set of events. That's exactly what we did above. The only thing that we additionally added here was we were allowed to have monadic predicates on the set of, on individual elements of T. And for the continuous time, then you have a structure for periods of time, intervals of time, which is an ordered triple of intervals, a set of intervals, and then two other binary relations, which allowed you to build the rest of the binary relations that you need for intervals. So you have both the precedence relation that you had from the point structure. So that is the correspondence between those two structures. And then you also have a binary relation of inclusion. So you can say whether one event is inside another event. With those things, you can then build the rest of the relationships that you can have, and they're quite a number when you get to continuous time. So we do need a mapping, it seems, between continuous time and discrete time inside phonology. I argued this with David Puppel and Virginie van Wassenhove some years ago, but it's also true so that we needed to go from some sort of representation in what looks like continuous time here through something that we don't know the whole details of into discrete phonological representations. And actually the same thing is true, although like it's kind of backgrounded in the articulatory phonology literature. So this is taken from Brauman and Goldstein in 1989, and they point out that there are sort of two representations that you can use inside articulatory phonology. The first one, I think we're all very familiar with, we've seen many times, where the events are intervals of time. And then the other one they suggested, which they called their point notation, is very similar to the idea that was expressed above, which is that you can represent these things that are extended in time in the interval representation. You can represent them as single points in the point representation. So when you do this, then you need a mapping essentially between the continuous numbers, let's say R, the real numbers, and something that's discrete like N. So the events are intervals on the real number line, let's say, and the events are instants, points in time on the natural numbers. So the usual construction of the natural numbers is with a number 0 and the successor function, but there is an alternative equivalent expectation due to a Polish mathematician in the 30s using just the precedence relation. So this is the better, we're better off you doing this. And then we can partially preserve this. So then we have an understanding of how it is that you're supposed to go back and forth between continuous representations and discrete representations, such that if m is less than n, that is, if m comes before n, then it's also the case that the interval that maps to m in some sense comes before the interval that n maps to. So x comes before y. So we can at least partially preserve this. So there's some mapping between these two things that allows the thing not to be just a free-for-all. So I don't know exactly what the thing is going to be, but essentially it's going to be something like, that events in the continuous time can't be things like picket fences or something. Like, so you've got to have some coherent interval of time. So there's some sort of continuity notion that's being imposed, and exactly what that is, I don't think we know. So the other thing is that you can define successor in terms of precedence in first order logic, and you can't do the reverse. So using S for the successor relation, X is immediately followed by Y if X comes before Y and there's nothing in between. That's what this says. Of course, you can never say that in the continuous numbers because there's always something in between. But if you do it the other way, you have to say that you can define the successor function, or you can define the precedence function in terms of the successor function as long as you already have the precedence relation. So like we've got, if X is succeeded by Z and Z precedes Y, then X precedes Y. Well, so we're using the thing on both sides. So this is this transitive closure of the successor function. This is not first order definable. So, because there can be an arbitrarily large number of points in between X and Y. So, the other way to do this is to think of this as a fixed point, which it is, and just to keep adding these things by triplets. So if you've got X, Y, and Z such that X is immediately followed by Z, which is immediately followed by Y, then you can conclude that X comes before Y. And you just keep doing this until you can't do it anymore. So like you do it until you reach equilibrium. That's the fixed point. Right. So you can sort of see this as logic with transitive closure. So first order logic with transitive closure can do this. This is also similar to Keynes' linear correspondence axiom. So you've got some sort of relationship in the syntax C command, that asymmetric C command that you want to map to order in the phonology, but the thing that we want here is this open precedence. Because the C command can also be long distance, and then so we don't mean that A has to immediately precede B if A asymmetrically C commands B. We just mean that it comes before it. And so for Kane, he wants a total order. We will drop that assumption. We will also drop the anti-symmetry. So we'll allow partial orders, and we'll allow loops, which Kane did not. So we're not going to end up with a string. In this case, we're going to end up with a graph. And you can go back and forth between sparser and more full representations. So these have the same reachability conditions, these two graphs. And so the graph on the right is the transitive reduction of the graph on the left, and the graph on the left is partial transitive closure of the graph on the right. So, this is an operation that probably is significant, although as yet we don't have any real evidence. But one possibility is, for instance, that you want to take the transitive reduction of a graph, and then that will be essentially how you're going to pronounce the graph. So the second argument is that reduplication is loops. This is the argument that was made in Eric's book. And so here is the representation for something like cat. We've already seen this sort of representation for the Algol example. And at the bottom is what I'll use to sort of represent what it is that reduplication is doing. So reduplication is, when it's a process or a morphological operation in a language, is looking for the thing that is mere as the final thing in the graph. So the thing that points to the end, and it's looking for the thing that is the first thing in the graph, the thing that the beginning event points to. And then we just want to add an arrow from the last thing in the graph to the first thing in the graph, right? The arrow from the T to the K here. This is the specification of this as a process. So the dotted lines in these cases will represent things that we're trying to match in the graph. I haven't put dotted lines on the beginning and the end symbols because by hypothesis, they're unique. So there is only one beginning symbol, and this gives you the binding between different representations. So suffixes, for instance, have an end symbol in them, and that will bind together with the end symbol in the graph that you're attaching to. So this tells you how to combine the two graphs together. So this says look for the beginning thing and the thing next to the thing that the beginning thing points to, which is the K in this case. So this will unify with the K, this will unify with the T, and then this solid line is the line that we add. So this is how we get from cat to cat cat. One of the most interesting things, I think, was a discovery made by Fitzpatrick in 2005 that you could easily do monom triplication. So monom usually has bisyllabic reduplication. So if you have a word like malipi, then the reduplicated form is malipi lipi. But there are a number, like a few dozen, of morphemes in the language that look like they're pre-reduplicated. And so ragogo is one of these. And when you reduplicate a form like ragogo, then you actually don't get ragogo gogo, you just get ragogo go. So it looks like the fact that it's sort of already reduplicated means that you don't do as much as you would have done before. And so the representation that we would have for the general reduplication pattern in Austronesian really generally is something where the last two syllables reduplicate. So schematically, just in C's and V's for now, this is what we would have. We'd be matching a CV sequence at the end of the word and then looping back to the first C. So in malipi, we would be looping back from the E to the L, and then we get malipi lipi. Now, this doesn't say that these, although, it's tempting to say, okay, well, then C1 has to be distinct from C2. Graph doesn't actually say that. You just have to find a node that will match with C1 such that V1 follows, and a node that will match with C2, which could be also C1, and then to V2. And in fact, that's what you have if you just take take it at its word. So take monom at its word. And so ragogo is then going to have a loop on go. And then when you sort of walk backwards to find the second to last consonant, so, here's a vowel, here's a consonant, then we can go back to the vowel, back to the consonant. So we want to add a link from the last vowel here back to the second to last consonant, which is the G. Also, still, it's the first to last consonant and the second to last. So the blue arc, with blue is just for expository purposes here. This gets added, and then, in fact, what you get is, you get triplication. So there, we make two roots back to the G. So we go through one and get rago, go, go, and then out. And so this gives us a derivation of the triplication facts. This is also the same relationship holds in compounds, where something that points to the end is linked back to something that points to the beginning. So when you take just the black and bird and just put them together so that the beginning and the end things are bound to each other, then you'll get what's in black at the top. So black and bird. And then in order to say blackbird, what we need to do is to connect the K back to the other B. And if you had bird black, if that were a thing, then we would be connecting the D back to the B. Now, I do think that these representations also have to be stored in memory. So, so blackbird and so on will ultimately be restored in memory with this sort of diagram would be the idea. And so it also, compounding, or if you prefer the other way around, reduplicants are like compounds in that they take the last thing and hook it to the first thing of something. And so when those two things are the same, you'll get a total reduplication. When those two things are separate things inside the diagram, you'll get a compound. It's also then necessary to have the same link when you do certain sorts of language games. So here's Pig Latin. So, Pig Latin for black is akble. And so you also need the K to the B relationship drawn in blue here as part of the game. So the game is obviously that you jump over the first string of consonants, if there is one, like so first consonant, to the vowel. And then you go to the end of the word, and then you go back to the beginning. And then when you would have gone to the vowel, you instead go out through A, right? So the blue stuff is the additional stuff that's added, the A is part of the language game. And so then to try to say that more generally, we will have a representation that looks like the top here, which says like we're looking for the first vowel. And in my particular dialect of Pig Latin, if it's vowel initial, then you say way. And so this green line, if this green line is here, then you use this green line. And if the blue line is here, then you add, if the blue dotted lines are here, then you add the blue lines in this. So I'm not, Max looked at this extensively in his thesis, this idea that that if you go this way, you have to go this way. Like, so the green goes with the green and the blue goes with the blue. I won't have anything more to say about this today, other than it appears that you need such things. And so then, you know, by applying this to black, then we'll get akble. The third argument, which I won't go into detail about today, which you can read in Max's thesis, is the idea that you can traverse these graphs in parallel when the individual events are compatible with one another. And so he uses this to analyze various cases of vowel harmony and tonal phenomena. And so in Turkish, for instance, we're getting a span that starts, which is both front and round from the ü. And so the individual vowels for Turkish will be specified for these things on separate events. So this is the reinterpretation of autosegmental phonology using these graphs. And this was the real amazing contribution that Max made, is to redo autosegmental phonology just by allowing these things to be said at the same time. You could, if you want, add another relationship of synchronicity or synchrony between these two things, but Max argues that you don't need it. So the idea is that as we're going through, these two things get said over top one another, and then you'll notice that there's a minus round specification that happens inside the span of this plus round specification. And Max argues that the innermost thing takes precedence. So you can be doing something and then you can change over and then you can come back to do the other thing. In this case, you don't ever come back. So we start out with a front round thing, and then it becomes a front thing. And even though we go back to a high thing here, we don't go back to having the round item. So, so this gets the well-known blocking effect of low vowels on rounding harmony in Turkish. So look at Max's thesis for that. We can also do non-concatenative morphology this way. So these look a lot like the compounding examples, except that now the way they get stitched together is more complicated. So take these sort of, you know, typical cases from Arabic where you want to say you have a root of KTB and you want to say that you have a vowel melody. So the answer is, and plus, you know, maybe a template. So then the answer is to just say that. So you say K is followed by T is followed by B. That doesn't mean that they have to follow immediately, right? So the interpretation of these arrows is as maybe next. And so from the beginning point, you could go to the K or you could go to the E. So we're going to need to figure out how to say a graph like this. And the usual thing is going to be adding extra information when you have situations like this where you could take one of two paths, then the language is going to tell you something about how you should do that. And there are many things that we already know about from universal grammar that will sort of help us with that. So here is likewise a graph that represents the syllable structure for Arabic. So Arabic words conform to this. So this is just to steal this idea basically from finite state morphology, where you will have things in finite state morphology. The items will be on the arcs. Here they're on the nodes. But you can encode very perspicuously a syllable structure like this, where you can have short or long syllables, light or heavy syllables. And then for the last syllable, you can have super heavy. So this will do that. When you apply that graph to the other graph, so when you combine them, then we will be adding the green lines for this purpose. So the green lines are essentially the syllable structure information. And now the red lines are obviated. Now, the color here is just so that you can follow what happened. So the black and red lines are the lines we had initially. The green lines are added by just doing syllable structure in this language. So those are the lines that are added to conform to the syllable structure. And then the red lines are the lines that you're not going to traverse now. So this will give you kitab. And whether you need to eliminate the red lines, probably not. But if you wanted to, then the idea would be that you can see here that there's a way to get to the E through the K now. And so this one is not necessary anymore. And you can follow that same logic through. And so that's the 3-node transitive reduction of the graph. So once we've added the green lines, then if you do the 3-node transitive reduction of the graph, that'll remove the red lines if we need to. It's not clear we need to. So you can also do this in FST. I will just leave this. So I won't go through this. You can look at it later, and email me if you want the code. It's like 5 lines long. So we can also do other non-concatenative morphologies. So like one famous one from German would be umlaut. And so we can just make the umlauting thing be just the feature that you want it to be. And now rather than just floating free for all, like, so the problem would be, how come if the front feature is floating, why does it go where it goes? And so now we can constrain partially its location by a precedence relation with the suffix that induces it. So we will draw these direct graphs in this way. And so now this can be pronounced on top of the U, for instance. Okay. You can also do this for like wilder sort of morphological things. So here's snurfing, which apparently means snow surfing. I didn't have this word before. So snow surfing, make the compound. And then the weird part about the blending is that you're allowed to add this line from the sn to the which of course I've just done with spelling here. And so there's obviously something to do with some sort of like idea that the first part of these two words are the same, and so they can be blended. So in this case, the S alongside the S, those could be collapsed. The idea would be because like you're going to an S, and then all you're doing is just merging these two nodes, which are non-distinct. So probably non-distinct merger is something we have to think about in terms of a graph operation that you can do. Another argument that I'll give is just that we need to represent sets of pronunciations. So words that have alternative pronunciations, here's neither and neither, but there are quite a lot of these in English actually. And, so you need some perspicuous way to do this. And so the maybe next allows you to actually characterize sets of strings. In fact, this was well known. This is exactly what the finite state technologies do. And subregular phonology for that matter, is they allow you to have sets of things through finite state diagrams. And so this is a simple finite state diagram for the alternative pronunciations of neither and neither. Max also discusses this in his thesis. Here's one for George Bush's famous nuclear as opposed to nuclear. Again, you need some sort of notion that if we say nucleal, then we're going to say lur, and nucleic, we don't say nucleic or whatever. So the U thing only goes with the R. I've also sort of offered a possible representation here for stems that don't occur as free forms. So nucleus, right? So here's the ending for the singular, nuclei, the ending for the plural, but nuclei is not, a form by itself. So we might want to have also, we could just fail to have a link from E to the end, or we might want to annotate that by saying, yeah, that's not a full form. So word families are possible with these things too. I think that this is a good suggestion about how people might learn them, learn the word families, and then this gives us the opportunity to represent the exceptionality of these forms directly in the graphs. So On that point, here's an example of an allomorphy. So as probably everyone knows, Korean has a nominative marker that varies according to whether the stem ends in a consonant or a vowel. It's E with consonants, Ka with vowels. So the way to say that is to have this thing at the side here where you're trying to match a consonant. If you can find a consonant that is at the end of the stem, then you'll add E to it. If instead you find a vowel that's at the end of the stem, you add Ka to it. And so the unification with a word like so is going to be on the vowel case, so that this one would be soka, right? And so this is what we're searching for, and it would find its match in the O there. And so then that'll bind it together. The E is still in the graph, but is unpronounceable because you can't reach it. The last argument that I'll give in this case will be under specification in time. And so I'm going to revisit an experiment that we did a long time ago now, where we were looking to try and see whether or not very young infants, 2-month-olds, 8 weeks old, could distinguish between ah, e, and oo. This was work that was originally done by Metzoff and Kuhl and later by Worker. And so we replicated those experiments and then sort of took it a step further. So we wanted to see whether they could also distinguish things that were more than a single vowel. So we started with we, and we were able to show that, yes, they could tell we from e. So they could tell ah from e from oo, ah from oo, e from we, and so on. And then we wanted to try two things that had more than one thing in the blank, so we wanted to try two syllables. So we tried you and we. These are at least like super high frequency syllables of English, given that they're pronouns. And the children couldn't do it. The 8-week-old, they could not tell you from we for some reason. And they were trying to match faces. So there was one audio stream, two faces, one articulating you, one articulating we, and they didn't match in this case. And moreover, in fact, like we then tried moving them. So we had the wrong face, like we had the we face for you, and played, and then had a foil face like E or ah, and then they would match the we audio with the U face, vice versa. So there seemed to be, we did really well. Then the person who was doing this with us, Rebecca Byer, she went to graduate school, but in electrical engineering. So so we stopped this. So we at the time said, well, look, what we want to say is something like, well, the thing that you and we share is that they're both syllables that have like high vowels all the way through, and then the glide and the vowel, and then they both contain round and they both contain front. So what we seem to be saying is that the infants don't know whether the rounding came before the frontness or the frontness came before the rounding. Okay, so that was our intuition. This graph notation now gives us a way of saying exactly that. So if we start out with this graph, so there's a syllable. The syllable consists of a glide followed by a vowel. It's high all the way through, and there's a rounding in the syllable, and there's frontness in the syllable. But we don't actually know what the order between round and front is. So that has to be established. Is it round then front, or is it front then round? Now, ultimately the children have to learn that you can't have round and like there are no round front vowels in English, but they will have to make that association later on. So the next later on step is that, let's say for we, they somehow figure out that the rounding and the consonant are sort of bound together, and the round is coming before the front. I don't know which of those goes first, but they have to figure out that rounding comes before frontness in we, and eventually I think they probably then collapse those into single events so that you have progressively more phoneme-like representation where you're aggregating together the features that you can so as to reduce the total number of events. So there's sort of a simplicity criterion on the events, on the size of the graph, basically. Okay, so there, I think, is like a lot more of this than people seem to think there is. So like, historically, there's diachronic change. that looks like metathesis or something very similar to it, or breaking, where you have front round vowels that break into round and front vowels, way or so. Do you get this, I think, in L2 perception? Certainly when I was doing field work as a student, I didn't know exactly what the order of things were. You'd get a rough draft as you transcribed the word for the first time, and then you would have the language consultant repeat the word, and you would go in and sort of check your understanding of that. It's also the case that there are some limits on the auditory perception of order. And as the sequences that are presented to people get longer, it becomes more and more difficult for them to detect them. So two-element sequence, this is work by Richard Warren. So two-element sequence like AB versus BA, you can tell this when the things are only 20 milliseconds long. But when you give people just random auditory events, signals, where you are trying to do ABCD versus ACBD, the threshold for this actually jumps tenfold, so that you need 200 milliseconds of duration for each of these items in order to be able to do this, except, as Warren points out, except in speech, where you don't need 200 milliseconds of duration for every segment in SP for spot. So you can do, in fact, the full syllable can be 200 milliseconds long, and we can do order inside syllables. So Warren thought that this was done with a sort of gestalt thing. My suggestion is the circuit diagram that I gave near the beginning of the talk. So the idea from all this is that we need to encode partial knowledge about order. Sometimes that's all that the person is able to take away from the situation, is just partial information about the order. And so we want some way to represent that. And so then that means that you're going to do morpheme recognition, as we sort of displayed before, on these open bigram matching, and that will work even if you didn't hear the whole thing perfectly. So this gives you a gradient match to the items in the lexicon, very similar to the way that we sort of think about string matching, except that it has certain redundancy built into it, and then it's going to make slightly different claims, which have to be computationally worked out and verified for different items where you would have different things missing. So it is the most important idea, though, is it's tolerant of insertions and deletions because of the open character of the bigrams, or because the basic representation is in terms of precedence. And so it's tolerant to things like epenthesis or deletions. So that's its sort of big win as far as I'm concerned. So the summary to finish up, so that I and not too far beyond the hour, is that the claim here is that the phonology is better thought of as graphs and not as strings, and that those graphs are really graphs composed of events, features, and precedents. So points in time, properties of points in time, and then precedence relation of maybe next between points in time. And this allows for the direct representation of a host of linguistic phenomena like reduplication, non-concatenative morphology, alternative pronunciations, and this sort of temporal underspecification that we see that I think is the source of historical metathesis and so on. All right, so thanks to many, many people, which I won't read off because this is being recorded, so you can look at it later and read them yourself. And thanks. Thanks, Eric.
Yeah, thank you very much, Bill. So even though we're right at the hour, I think we have a little bit of time for questions. So one question, the one question from the audience asked if you could go back over the trigram argument from Pinker and Prince.
Yeah, sure. So I'll reshare the screen and then find that.
Yeah.
Okay. Okay, so the argument that Pinker and Prince offered, and so the proposal that Wayne Rickogren made in '69 was to have what he called context-sensitive coding for phonemes. And so what he wanted to say at that time was that, so the way he would have written this is to say that the A at the beginning of Algol was in the context of the word boundary on its left and the L on its right. So the idea was that this is the simplest context that you could have, where you had both a left context and a right context, is a single phoneme of context on both sides. And so this was adopted by Rumelhart and McClelland, and their reasons for adopting this in their study of the English past tense. So they were trying to train a neural network, a lot smaller than current neural networks. They were trying to train a neural network to learn the past tense of a form based on training examples. So they were given, input-output pairs. So this is the infinitive, I think they gave it, and here's the past tense form for the verb. And so what they wanted, a representation for the words that was not a string, so it was not variable length, and was a fixed encoding. So exactly those properties that I was saying before were the properties that motivated Rumelhart and McClelland. So you wanted to take something where in theory, the verb could be really small or really big, could be one syllable, several syllables. And they wanted a way of representing the contents of that string as a set. And so by doing it as a set, you can pre-calculate all of the potential members of the set. And you'll have a node in the neural network that will be for each of those things. So the idea is here that the set of items that you have in Algol by trigram. So we'll just walk through the thing and we'll say, what is the trigram for the first symbol? What is it for the second symbol? What is it for the third symbol? What is it for the fourth symbol? What is it for the fifth symbol? So for the first symbol, it finds itself sandwiched between the beginning of the word and the L. So that's this L. And then the L finds itself, the first L, between an A and a G. The G finds itself between an L and an A. And then the second A finds itself between a G and an L. And then the last L finds itself between an A and the word boundary. So this is a representation of the sliding 3-character window as we go across the form. So, as we move across the form from left to right, and just you can imagine that there's a number sign at the beginning and a percent sign at the end, then the 3 characters that we see as we slide the window across are number sign AL, ALG, LGA, GAL, AL, word boundary. So, so this is the set of things that we saw. Now we do the same calculation on this reduplicated form, and this is the set we get, which is the same set as this one. So Pinker and Prince said, well, look, if you use a set of trigrams, then you're not going to be able to represent the difference between Algol and Algolgol. But we know you have to represent that difference because languages do reduplication. And so then in the languages that do reduplication, or even in English, the Algol is not the same word as Algolgol. And so then they, had a proof that says that if you use 5 grams, that you would need a repetition of so many characters before you would not be able to tell that anymore, and so on and so forth. So, so the argument here rests on the notion that this is a set. So, and that was exactly what Wickelgren had proposed, and it is what Rumelhart and McClelland used. So if you only use a set representation, that is, no multiplicities are allowed. So like if we added another, so if we go back, to get Algolgol, once we sort of do it with the graph, if we're going back from the L to the G, right, to get Algolgol, this one. So if we're going back from the L to the G, then we would have another thing where we said, oh, well, the G found itself between L and A. So the L went back to the G and then it's going to the A. So we would have another LGA element. But having a second LGA element in a set doesn't change the set because it's a set. And so then there is another data structure available to you in computer science or mathematics, which is simply called a multiset, or in computer science things, it's usually a bag. And that's really the argument, is that if you change your representation, maybe it's simpler to think it from here, if you change your representation from a set to a bag so that you're allowed to have 3 instances of AL, in this case, 2 instances of LG and 2 instances of GA, which is this graph here, where going from Boston, like, if you want to think about it in terms of the flight diagrams that I was giving, there can be more than one flight from Boston to San Francisco. So this is sort of saying the same thing here. There can be more than one road from A to L, as it were. And in fact, in this case, there are 3 of them. And so the multiplicities that are allowed in the multiset or the bag, these are the difference between having a set and having a multiset. That is exactly the difference between having a set and a multiset. And so if you allow multisets, then the problem goes away. So the Pinker and Prince problem is predicated on the idea that the representations are sets and not multisets.
All right, wonderful. Thank you very much for that explanation. So we are now at about 1 hour and 10 minutes. And I think one of the beautiful things about Aprender ao Vivo is that this will exist as long as the internet does. Let's thank Bill and the Brazilian Linguistics Association again for this opportunity. There's contact information in the slides. And so if you're watching this sometime into the future, hello, future people, you know how to get a hold of Bill and myself too. So thank you again, Bill, and thank you, Abralin ao Vivo. My apologies for my poor Portuguese.
Well, I have no Portuguese. So thank you, Eric. Thank you, everyone watching. Thank you, everyone in the future. Thank you, everyone in the past, too.
Yeah, thank everybody.
Great. Thanks, everyone. Okay.